Continuing with 4.9, find the coordinates of any points where this function has a horizontal tangent line. As soon as we see tangent, we know that implies we're taking the derivative. So it looks like we have a product of two functions, so we're going to use the product rule here. Alright, so the first times the derivative of the second, which is just e to the x, plus the second times the derivative of the first, which would just be 1. Right, we're trying to see where that has a horizontal tangent, and remember, it would have a horizontal tangent line when the slope is equal to 0. So our numerator, if we have a fraction, okay, that's just a reminder there. So where is this equal to 0? It might help to factor this, so I'm going to go ahead and do that, x plus 1. Okay, so set each part equal to 0. Alright, so we have e to the x equal to 0. That is never going to equal 0. If you know the graph, you know there's a horizontal asymptote there. If you know anything about exponential functions, that will never be 0. So I'm going to just write none there. Alright, this one, it looks like x equals negative 1 would make that 0. And we're trying to find the coordinates of any point. So plug that in. F of negative 1 would be negative 1 times e to the negative 1. Or I could write it as negative 1 over e. Alright, so that would be my point. Negative 1, negative 1 over e. And it's that simple to start off our day. Alright, moving on to example 7. Find the equation of the tangent line again. Here. Alright, so there are two ways to do this. Take a look at this. You'll start to pick out these things as you do more, but I noticed each of those has an e to the x. So I could factor that out. If I do that, I end up with the product of two functions rather than two product rules. So I don't care which way you do it. Alright, I'm going to choose to do it this way just because I think that it might be a little bit shorter. Alright, so dy dx, it's derivative of y, equals the first times the derivative of the second, which would be 2x minus 2, plus the second function times the derivative of the first. And we know that the derivative of the first is just e to the x. And we're trying to find the equation of the tangent line at this point. So we can plug in, actually maybe we should, yeah, let's distribute this out. Maybe we could clean it up a little because that's a lot to plug into right now. Alright, minus 2e to the x plus e to the x times x squared minus e to the x times 2x plus 2e to the x. Alright, and don't forget dy dx equals. So if you take a look at this, we have an e to the x times 2x. We have a minus e to the x times 2x. We have a minus 2e to the x plus 2e to the x. So we just, by simplifying first before we plug into our point, we made this a little bit shorter. So we have e to the x times x squared. Alright, so now if we would like to evaluate this, dy dx, we're going to show what we're doing. We are evaluating this at x equals 1. Plug that in. We get e to the 1 times 1 squared, which is just e. Alright, and we were supposed to find the equation of the tangent line. So y equals our y value plus our slope times x minus 1. That would be the equation of our tangent line. Alright, if I went a little further and asked you for the normal line, the equation of the normal line, the only thing that changes is our slope. Remember, a tangent and a normal line have opposite reciprocal slopes. So this would be all that would change for that. And again, it didn't ask for that, but why not review it? Alright, moving on, example 8 here. find dy dx for that function. Alright, so take the derivative. So our original exponential function times the derivative of the exponent. Here we have to use the product rule. So the first times the derivative of the second plus the second times the derivative of the first, which would just be 1, plus 2x minus 2y dy dx equals the derivative of 10 is 0. So we're trying to find dy dx, so we are going to have to solve. Alright, we can't just leave it here. So I'm going to expand this out. So I get e to the xy times x dy dx. Alright, plus e to the xy times y plus 2x minus 2y dy dx equals 0. Alright, move anything with dy dx to one side. Move everything else to the other side. If you do this differently than me, your signs might all be different, and there's nothing wrong with that. Alright, so I'm going to go ahead and keep anything with dy dx over here. So this term, and I also have a negative 2y dy dx. And I'm going to move everything else to the other side. So I'm going to have a negative 2x. Okay, come on. Negative 2x minus e to the xy. Come on. Times y. Okay, I have two more steps here. Dy dx. Factor that out of those terms. E to the xy times x minus 2y equals, and we still have this side over here, 2x, or negative 2x minus e to the xy times y. Last step is to divide both sides by this function, so I get dy dx equals negative 2x minus, and I'm just going to put the y in the front, y times e to the xy all over. Same thing down here, I'm going to put the x in the front, x e to the xy, okay, minus 2y. And again, if you moved your dy dx's to the other side and everything else to the left, your signs would all be different, which is, there's nothing wrong with that. Alright, keep going. Here we need to find the second derivative. Alright. So there are two ways of approaching this problem. We can leave it as the product rule, which I think that most of you like a little bit better. Or you could rewrite this and use the quotient rule. So, oh, that wouldn't be negative anymore. Okay. Or you could rewrite that and use the quotient rule. So it's up to you, whatever way you want to approach this. So we have the first derivative. I'm just going to go ahead and use the product rule. So we have the first, and this is going to take up a lot of space. There's going to be a lot of ways of rewriting this. So I'm just going to write it all out, and you can choose to simplify it. Alright, so the first times the derivative of the second. So we have an exponential function, so we just rewrite it, times the ln of the base, times the derivative, oh, that's a 3, times the derivative, negative 3, of the exponent. Alright, plus the second function times the derivative of the first, which would be 2x. Or not 2x, would it? It would just be 2. Okay. Don't want to mess that up. Alright, maybe we should clean some of this up. Maybe we shouldn't. It's up to you. I'm just going to rewrite it a little bit, because I don't like putting this negative 3 back here, because I think I'm going to forget it. So I'm going to move it up front. Negative 3 ln of 5 times 3 plus 2x times 5 to the negative 3x. And I'm going to write the 2 right in the front. That's a 2. Alright, times, don't mix that up. Don't multiply this. Negative, okay, there we go. Now we just have to take the second derivative here. And hopefully I did this all right. I think it looks good. Alright, so this whole part, this is just a constant. So I'm going to just write that down so I don't have to worry about it anymore. Alright, now I'm going to do the derivative of this part. So again, we have the first times the derivative of the second. So that would be 5 to the negative 3x times the ln of 5 times the derivative of the exponent, which would be negative 3x. Oh, can't close that parenthesis yet. Alright, because I forgot to do the other part. Plus the second function times the derivative of the first, which would be just 2x. Or 2. I don't know why I keep thinking 2x. Alright, now I finished that part. And last I have to do this part. So we have plus, and I'm just going to leave that constant right on the outside. The exponential function times the derivative, or the ln of the base, times the derivative of the exponent, right, which is negative 3. And again, I could clean this up. I probably should. Alright, there's a negative 3, negative, would have to distribute this or rearrange it. Okay, I'm okay with you leaving it just like that. If you want to try to simplify it, there's a lot of things you could do here. Alright, but I'm not going to take that time. So we're on to our last example. Nothing's better than a glass of cold milk, right, from the refrigerator. Alright, here's our function. We have an exponential function. And let's see, if we sketch a quick graph of that, it would look something, right, it starts out kind of, it looks like, and I know a little bit more maybe about this than you do, but you'll learn. Looks like the maximum it could be is 72, because then this, even if this goes really high, this is making it smaller. Alright, so if I was going to sketch a graph of this, it would look something like that. Whoa. A little more smooth than that. Alright, so let's take a look at this here. What's the temperature of the refrigerator? Alright, so the milk started out in the refrigerator. So if we look at t equals 0 and plug that in, we get 72. Actually, maybe let me show you what I'm doing. Alright, at t equals 0, so we're looking at the y of 0. We get 72 minus 30 times anything to the 0 power is 1. So we get y of 0 equals 42. So the temperature of the refrigerator is 42 degrees Fahrenheit. And how can we tell that's the initial temperature? Right, initial temp. What is the temperature of the room? So if we let this go on and on and on and on, the highest it's going to get is 72 degrees Fahrenheit, and I can tell because I know that that is the horizontal asymptote. And as a quick review, if we let t go to infinity of our original function of, I guess I'll call this y of t. Alright, if we let t go to an infinity, we're going to get a maximum of 72. So there's a horizontal asymptote there. Alright, when is the milk warming up the fastest? Anytime we're talking about a rate of change, we're talking about a derivative. So when is the milk warming up the fastest? That would be at t equals 0. And how do I know that? Because that would be the slope of this. Oh, this is a terrible function. It should be more around. All right. So the slope of that function, y prime, is the steepest there, or the greatest, is the greatest. All right. Y prime is the greatest. The y function is the steepest, right at the beginning point, and then it kind of levels out a little bit. Determine algebraically when the temperature of the milk reaches 55 degrees. I don't know if I'm going to have room to write it in there, so I'm going to write it right down here, letter D. So I'm trying to figure out when the temperature will reach 55 degrees. So 72 minus 30 times 0.98 t to the t. Alright, solving this, I get negative, if I subtract 72 from both sides, I get negative 17 equals negative 30 times 0.98 to the t. Divide both sides by negative 30. Get 17 over 30 equals 0.98 t, to the t, sorry. Now, to get that out of the exponent, we're going to have to take the log, or the ln, of both sides. Alright, I'm going to choose to take the ln just because it's less writing, and I like that. Natural log. It's always better to go natural, right? Alright, so we have this 0.98 to the t. And if you remember, we can, if it's in the exponent of an ln, we can move it right to the front. So ln of 17 over 30. Oh, that does not look like 17 over 30. Alright, 17 over 30, there we go, equals t times the ln of 0.98. Alright, so the last step then would just be to divide. Oops, t equals exactly ln of 17 over 30 divided by ln of 0.98. So that is the exact value. If you wanted to get an approximation, I would say type that into your calculator, right? And type it in and leave it there, because we're going to use it in a little bit. And I think that we get about 28.114, because we always go 3 decimal places. And t was in minutes. So, does that make sense? So about a half an hour later, it went from 42 degrees to 55. That seems pretty reasonable. Alright, and then our last question, at what rate is the milk warming when the temperature is 55 degrees? So we're talking about a rate, so we know that has to do with the derivative. Alright, so we're going to have to take the derivative of our function, y prime. So 72, that's just a constant. So we have negative 30, that's a constant for our exponential part, times 0.98 to the t times the ln of 0.98 times the derivative of our exponent, which would just be 1. Alright, so we need to find at what rate is the milk warming when the temperature is 55. So don't be tempted to type in 55 here. We're talking, that's a time. Alright, so we have to plug in the time value that we have. Alright, and that's why you kept it in your calculator, you didn't clear it out. So I'm going to just write this, because you're not typing in exactly that point. Use the exact value in your calculator. Alright, type that in, and you will get an exact value. I'm going to just get an approximation right now so we can answer the question. So about 0.343 degrees Fahrenheit per minute, because we took the derivative. See, I wrote y prime. Maybe that's not the best way of doing it. If I wrote dy dt, y was in degrees Fahrenheit, t was in minutes. That helps us see what units we would use here. Alright, so then answer the question in a complete sentence. So at t equals, or t is about equal to 28.114 minutes, minutes, okay, comma, the milk's temperature, alright, is it increasing or decreasing? Well, this is positive, so we'd say increasing. At a rate of we're almost finished here, at a rate of 0.30 or 0.343 degrees Fahrenheit per minute. Alright, so not bad. I know this was kind of a longer video. Talk about the important things in your whisk. If you want to try a problem or two, go for it. You know that would never make me mad. Alright, have a great day.